This section is called Autonomous Differential Equations and Population Dynamics. Population dynamics is really an application of autonomous differential equations, so I'm going to take a look at what autonomous differential equations are first in this video, and then I'll make a different video for the population dynamics. In fact, I'll probably make two, possibly even three. Autonomous differential equations are just differential equations that take a particular form. We're already familiar with a couple of forms of differential equations. One like this, y prime plus a function of t times y, which remember is also a function of t, but specifically the function y, is equal to g of t, another function of t. The difference between this function of t and this function of t is that this one is multiplied by y, and this one's not. This is the one that's on the right-hand side. This one we called a linear first-order differential equation. This one, y prime is equal to a function in terms of t times another function in terms of y. We call those separable because they can be separated and integrated. Separable differential equations. And the kind that we're going to be looking at in this video are, I should have a y prime there. Y prime is equal to g of y. The difference between these two is the function f of t in this form. There's no function f of t in this form. Now, y is itself a function of t, but here we have a function of t explicitly, and in this one we don't. So these are called autonomous differential equations. And something I'd like to point out here is that because these two are so similar, we can say, for example, I'll write this in and then I'll erase it because it's not strictly necessary, that the function f of t is just 1. And so this function, or sorry, this differential equation is a separable differential equation where the function f of t is just a constant, 1. So every autonomous differential equation is also a separable differential equation. I'll say that again. Every autonomous differential equation is also separable. It's a subclass or a subcategory. So one way to solve autonomous differential equations is by separating the variables. That's not what we're going to be doing in this video, although we might use that approach to confirm some solutions, but we'll just have to cross that bridge when we come to it. All right, I'm going to erase my 1 here because I don't want that anymore. Every autonomous differential equation is also a separable differential equation. Okay, let's take a look at an example of an autonomous differential equation. Y prime equals y. All right, this is, let me find my pointer. This is a function of y. It's the simplest function. Well, maybe a constant would be simpler, but short of that, this is the simplest function of y there is. So this is the simplest autonomous differential equation there is. To solve this, we can treat it simply as a separable differential equation. We can rewrite this as dy dt equals y, then divide both sides by y and multiply both sides by dt. So I get 1 over y equals dt, and then integrate both sides. This is going to give me ln of y equals t plus c. And if I exponentiate both sides, I get y equals e to the t plus c, or y equals k e to the t. We've done this one before, or one very much like it. So if the details here are lost on you, then please go back and take a look at another video. Essentially, I've raised both sides of this equation. I've made both sides of this equation an exponent on e. I've exponentiated. E to this power is just y, and then from this step down to here, e to the t. This is e to the t plus c, which can be written as e to the t times e to the c, and e to the c is a constant, and I tend to call that k. So this is the solution, the general solution to this differential equation. So I'm going to rewrite that solution up here. Y equals k e to the t, and then I'm going to erase most of the work that I've done down here to give myself some more space. And then I'm going to cover up this solution. I'm going to say for the moment that we don't know what that solution is. Well, if that's the case and we didn't have a way to find the solution, then how might we go about figuring out what the thing looks like? And one answer to that question might be to try to graph it. Not quite as we're used to doing. Normally when we graph, we have an independent variable, an axis for the independent variable here. That would be t. Put that there for now. And this would be y for the dependent variable. But we don't have that information. We don't have a function of y in terms of t. All we have is some kind of a differential equation function where we might consider y the independent variable and y prime the dependent variable. Well, normally our independent variable is x and our dependent variable is y. So we could think of this as y equals x in order to graph it. That would give us a graph that looks something like this. That's a little off. It's not quite a 45-degree angle, is it? But it'll do for now. That is not what we have. This is the graph of y equals x, right, in green here. But that's only true if this is the x-axis and this is the y-axis. The relationship is the same, however. My input is y and my output is y prime. So I'm going to get the same graph. I've just labeled my axes differently. So I can erase this because that's not really what I have. What I do have is the graph of y prime equals y. For every y value, the y prime value is the same. Let me plot a couple of points on here. Let me go for this one. That's going to be important. And then I suppose I should have a scale here. I don't know what size of screen you might be watching this on. The screen that I'm creating this video on is fairly small. It's smaller than a laptop. It's a smallish iPad screen, and so I feel like I can see this okay, but I don't know what size of screen you're going to be watching it on. I have noticed that some of my videos get a little blurry if you blow them up too much, and that may be a resolution thing on my part. I'll look into that. But this should look pretty good on a laptop or an iPad screen or a tablet screen. It may look a little blurry if you go full screen on a big monitor. Anyway, these tick marks, we'll just call these, we'll say each one of these is 1. And so I'm going to pick some points, 1, 1, 2, 2. Let's go with -1, -1, and -2, -2. Those should do. And then let's talk a little bit about what this is telling us. What I'm graphing here essentially is for a given value of y. Let me draw another set of axes down here because I'm going to need these anyway. These ones are going to be t against y. But up here, I'm saying that for every value of y, I can tell you what the slope is of the function y. Because dy dt, sorry, y prime, just means dy dt, and that's slope, right? So what we're going to create down here is a slope field, but we don't have the function from which to do it. So all we can do is use the differential equation. All right, so what does this mean? Well, if t, I'll put some tick marks on here, give myself some scale. Sorry to make you watch that. Take a look at, let's just grab a point here. This is the point 1, 1. But it's the point where y is 1. And what we're saying by this graph is that when y is 1, the slope of the function y prime dy dt is also 1. So that means that for every value of t, as long as y is 1, the slope of my function, the slope of my my actual graph, is going to be 1. So for every value of t, I'm using integer values here, but you can use whatever values you want, right? The slope there is 1. For every value of t where y is 2, the slope is 2. My scale is off here. That's supposed to be the 0.22. I'll just label it that. So when y is 2, the slope of my function is also 2. So when y is 2 down here, the slope, no matter what t is, the slope is going to be 2. Now, I'm kind of not doing a very good job here. It's kind of hard to draw a slope of 2 on a very tiny line segment, but that is essentially what's going on here. If I went out even further and said that when y is 3, what would the slope be? That would also be 3. So when y is 3, my slope is steeper still. Now, I doubt it's really actually that steep, but you get the idea. Down here, when y is -1, the slope is also -1, and when y is -2, the slope is -2. So I'll draw some of those in. That's what it looks like when y is -1. When y is -2, and I haven't done a very good job here, but that last line is when y is -3. What about when y is 0? When y is 0, the y value is 0 is right here. The slope is also 0. So I can add a line here. Let me make this pen a little bit thicker for this particular one. My little slope indicators that for every value of t, when y is 0, the slope of my function is going to be 0. Now, the purpose of this exercise was to say, if I don't know how to find the solution to this equation, this differential equation, how can I use the information that I do have to figure out what the equation might look like? And here's the answer to that. If I grab one of these, I'm going to start maybe here, and I'm going to use the direction that that slope sends me off in to sort of trace my way through one of these patterns, right? And if I go back in this direction, I end up doing something like that. Let's do the one where t equals 0 and y equals 1. If we start here and trace, we end up with something that looks like this. And I hope that you can see that very quickly begins to look like an exponential function. Down here, I'm going to get something that looks kind of like that. And that's what happens when you have, for example, y equals negative, looks like maybe -3 e to the t. That's this particular graph down here. There's one I'd particularly like to point out, and that is this one here. I'm going to make it really, like a really thick pen here. When y equals 0, for every value of t, then I get this function, I get this graph, right? When y equals 0, the graph looks like that. And that is the graph for the equation y equals 0 times e to the t, or just y equals 0. I got that from when y equals 0 here, y prime equals 0, the slope equals 0. So when y equals 0 down here, no matter what t is, along the t-axis, which is where y equals 0, the slope is 0. My little slope marks help me figure out that that didn't change all the way along that axis. And so my that particular case gives me the horizontal line, y equals 0. So you can see from this graph now that the solutions to our differential equation are very likely the exponential function, right, for varying different values of k. That's the family of exponentials. This one here again, the case where k equals 0, that's got a special name. We call that an equilibrium solution. And it happens where y equals 0. It happens here. There can be more than one. Depending on the differential equation, the family solutions can have more than one equilibrium solution. In this case, we only have one. But it comes from this position on my slope graph. I have a slope graph here and a slope field here. My graph of the slope tells me where the slope, y prime, is 0. it's when y is 0. So that tells me that the slope is 0 when y is 0, and that's my equilibrium solution. The equilibrium solutions come from essentially, this would be our x-intercepts, right? But because of the way we've graphed this, it's our y-intercepts. It comes from the intercepts of the horizontal axis. So what is an equilibrium solution? What is equilibrium? Well, if you've had physics, possibly if you've had higher calculus, you may have met that word before. It's essentially, and this is very much a layperson's definition, but it's essentially a kind of balancing point, right? If you imagine yourself walking up a hill, it takes energy to walk up the hill, right? Positive energy. You have to expend energy. You have to push yourself up the hill. When you get to the top and start down the other side, you also have to expend energy, but it's a kind of negative energy, right? You have to keep yourself up. You have to prevent yourself from falling due to gravity. At the very top of the hill, though, there's just an instant when you're neither climbing nor descending. You're neither expending positive energy nor negative energy. And so just for that instant, you are at what we call an equilibrium state. So that's like I said, just kind of a graphic sort of layperson's description of what equilibrium means. It's really all we need for this course. If it turns out we do need more, then I'll go into more detail later on. But for now, I think that's probably really all you need to understand. There are different kinds of equilibrium, and we'll talk more about those in a future video. For this one, I feel like I'm done with this example. I'd like to do another example, though, of an equation where we actually, let me see if I can move this square out of the way. This confirms, right? Wrong pen. This confirms our solution. We have exponential functions, several of them, for varying different values of k. This one's where k is 0, this one's where k equals maybe about -3, and so on. Let's take a look at another example in which it might not be quite so straightforward to solve the thing, but we can get an idea of what the equation's solutions would look like graphically by using this technique. Okay, here's a new differential equation. Y prime equals y squared minus 4y. I could, of course, write that as dy dt equals y squared minus 4y. And I could solve it because, since this is strictly a function of y, there are no visible t's here. But y is a function of t, but there are no visible t's. So this is a function strictly of y, and that makes it an autonomous differential equation. But because it's an autonomous differential equation, it's also separable. So I could treat it like this and use separation of variables to rewrite the problem and solve it. I think what I'd like to do is use the technique first that I've just shown you to demonstrate why we might find it useful, and then go back and take a look at the solution to this. So let me erase this version of the problem because I'm not actually going to use that at the moment. What I am going to use is a graph of y against y prime. So y goes here, y prime goes here. And I'm treating this as though this were x and this were y. And if that were the case, then this would be the function y equals x squared minus 4x. And this I can graph, well, there are probably a couple different ways I could complete the square. Let's do it both ways because we get different information from the two different techniques here. I can factor this. I'm going to get x minus 4. And that tells me where the roots are. Put some scale marks down here. Okay, so I have a root at 4, a 0 at 0, and 1 at 4. So there's 1 there. And then if I use completing the square, I get x squared minus 4x. Half of 4 is 2. 2 squared is 4. So I'm going to add 4 and subtract 4. And that gives me x minus 2. That's this part factored, squared, minus 4. So my vertex is at 2, -4. So I need scale markers here as well. So I've got a vertex here. This is a quadratic. It opens up because of the positive leading coefficient, And so I have something that looks vaguely like this. And I'm going to go back now in and erase all of my yellow stuff, because, well, not all of it. I want my roots here. This is not really what I was graphing, right? I was not graphing x against y. I was graphing y against y prime. So let's get rid of a little bit of this misleading stuff. And then I'm going to make the argument that actually it would have been better, my pen's not working, not to do this quite like this, but to do it instead as y prime equals y squared minus 4y, which equals y times y minus 4, or which equals y minus 2 squared minus 4. I did it using x and y here because I know that's familiar territory for you. Going forward, I'm going to be doing it this way because I don't want to forget what I'm actually doing, right? This is not actually what I was graphing. I simply used techniques from earlier algebra courses to get at the shape of the graph here. So in the future, I'll be using more correct terminology, if you will. So I'm going to leave this one here for now, just because it will remind us where we got the information that we have. Now, why did we graph this thing in the first place? We graphed it because it tells us something about the slopes of the original function y. When we know y now, we can determine what the slopes are, or what the slope is for any given value of y. Let's go ahead and create a graph of t against y. And then let's take a look at what's happening for the various different slope values, for the various different y values. What are the slopes for our various different y values? When y is 0, let's go ahead and do those first because I think they'll be the easiest. When y is 0, the slope is 0. And when y is 4, the slope is 0. Remember, this is a graph of the slope of the function y. So when y is 0, the slope is 0, and when y is 4, the slope is 0. So at y equals 0 and at y equals 4, let's put some, I'm going to need more space than that. Let's try this. There's y equals 4. I don't know how much more space, but I know I'm going to need a little more than I was going to give myself there. When y equals 4, the slope of the graph is 4. So no matter what t is, regardless of what t is, if y is 4, all along here, right, for every value of t, when y is 4, the slope is 0. So that means I can put a little, just a piece of a tangent line where the tangent line is has a slope of 0 at every value of t. This is a little overkill. But for every value of t, as long as y is 4, the slope is going to be 0 there. And the same is true for when y equals 0. Here's where y equals 2, where y equals 1, y equals 0, where y equals 0. The slope is actually also 0. So I'm going to have little slope markers all along my t-axis, because that is what my graph of the slope. This is my slope graph. This is my slope field. This is my slope graph. This is the graph of the slope values. And the y value associated with 0 gives me a slope value of 0. So when y is 0, the slope is 0, regardless of t. All right, now let's take a look at the 3 areas in between. So we've got y values larger than 4, y values smaller than 0, and y values between 0 and 4. Let's go ahead and do this section first. The y values between 0 and 4 correspond on the graph to the y values here between 0 and 4. And so that's this part of my parabola. This is telling me about the slope of the graphs, the function that I'm trying to graph over here. So if I look at the slope, if I look at this graph here, let's pick an obvious point. Let's go to the vertex. This is where y equals 2. And so I'm looking on this graph at where y equals 2. What's happening there is that the slopes are all below the y-axis, so they're all negative, right? Here's the slope is 1, the slope is 2, the slope is 3. Here all my slopes are negative. So if the graph of the slope falls below the y-axis, then I'm getting negative slopes. So all the slopes in this region here, because of all the slopes showing from here, they're all going to be negative. But at 2, they are the greatest negative. At 0, or just past 0, they're negative, but they're very small negative, so they'll be very shallow. Then they get steeper and steeper, always negative, until they get to 2. Then they start getting shallower again until they get to almost 0. So I'm going to graph this one first. I have a slope of -4 when y is 2. Over here, that's when y is 2, I have slopes of -4. So they're going to look something like this. Kind of exaggerating. I think that's about -4. That's really all you need for these. Of course, if you're going to do these on a computer, you're going to get more accurate slopes. But just think about, this is about down 4 and over 1. It's very approximate, but it's realistically approximate. Okay. Let's just take a look at when y is 1. We have slopes that are not as steep as this, but not close to 0 either. They're somewhere in between. So when y is -1, when y is -1, nope, I lied. When y is 1, I have negative slopes. So when y is 1, I have negative slopes, but not as steep as the previous line. And I'll just put some more in here. Not doing a very good job here. Okay, when y is 3, same thing. In fact, they're going to have the same steepness, right? Their steepness is going to be about -2.5, I guess, right? When y is 3 as well. So they're not as steep as they were at y equals 2, but they're steeper than they are if you go all the way back to y equals 0 or y equals 4. So now if I were to grab and trace out a line or a curve based on these slopes, we have something that looks kind of like this, almost 0 and then steeper still and then more shallow and then almost 0. So that's one possibility of a curve that I can see from graphing using the slope field. All right, so I'm getting a sense of what the graph of the functions look like, the family of functions looks like, by graphing the slope field based on the slope graph. Okay, now we need to look at so far we've talked about this piece of the slope graph, which gives us this piece of the slope field. But now we need to talk about the rest of the slope graph. What's going on to the left of y equals 0 and to the right of y equals 4. To the left of y equals 0 here is the same as below y equals 0 here. So let's talk about that piece next. To the left of y equals 0 here, my slopes are, first of all, they're all above this horizontal axis now, so they're going to be positive. But they start small, and then as y goes farther to the left, as y gets smaller, the slopes get steeper. So I'm going to have positive shallow slopes for things like y equals -1. Put these ones over here as well. At y equals -2, I'm back here a little bit, my slopes are really quite steep, but they're positive. Right? They're still positive at this point. So I'm going to have something maybe that looks a little bit like this. Again, this is not highly accurate, but it's approximately accurate. And I'm still analyzing the graph here to tell me what the slope field looks like here. I'm thinking about it, and I'm trying to be as accurate as I can reasonably for the short amount of time I have to work on this. Let's do one more here. It's going to be difficult because I don't have to go very far to the left here to get very steep graphs very steep slopes for my graph, so I'll just do y equals -3, and I'll try to make those look almost vertical. Of course, they're not, because this is not an asymptotic graph, but very close to vertical. Okay, so down here, what's happening? It's maybe something kind of like that. Okay. And then the last area is this piece up, because this goes down now to y equals infinity, negative infinity, right? So I'm going down forever. And I can only do so much of that before it's not practical to continue, right? My graphs would just get closer and closer to vertical slopes here, but never actually achieve that. So I'm going to leave that piece. And I'm going to do the same thing over here now, where y is greater than 4. And I get the same thing. Not too much to the right of y equals 4. My graphs are my slopes are going to be so high, so large positive, that they're not even on this slope graph. So I can start with when y is just a little bit more than 4, my slopes are positive. And they're already, they're fairly small. So maybe have some sort of shallow slopes, but positive. And then quite quickly, they get fairly steep again. So I've got this, and then if I go out by 3, my slopes are almost vertical. Okay, so there's my slope field, and let's grab one piece of this graph and see what does it look like. It's doing something like that. Now each one of these, this piece right here, this piece down here, and this piece here, each one of these is a separate, different potential solution to this differential equation. If I start in a different place and follow a different path, then I would get yet another potential different solution. And there are a couple that I haven't highlighted here, but I've left them to last kind of on purpose, because they're quite important, but also they're easy to miss. And so I really wanted to stop and come back to them and highlight them. And those are the equilibrium solutions. So I'm going to have one, make my pen just a little bit thicker here. I'm going to have one here, and I'm going to have one here. And I can see those a couple of different ways. One is that my graph of this function here, which I obtained by doing some algebra, the two places where y equals 0 here are the two places where y prime is 0, right? The two places on the y-axis, 0 and 4, which return a y prime value of 0. That's telling me that the slope is 0. So the slope field with little horizontal marks here, that's this. This is one of those. This is one solution, right? And this is another solution. So I'm going to make a note over here that the equilibrium solutions are y equals 4 and y equals 0. Now in this case, we have a couple of different kinds of equilibrium solutions. I mentioned on the last slide that there can be more than one equilibrium solution, and that's clear here. We have one at y equals 0, we have another one at y equals 4. But in addition to that, we have a couple of different kinds of equilibrium solutions. In this case, y equals 0, you can see that all the little tick marks, all the potential solutions are moving towards that equilibrium solution, right? They're all coming down and moving towards it. So we call that a stable equilibrium. Y equals 0 is an equilibrium solution, and particularly it's a stable equilibrium. Y equals 4, on the other hand, all of our solutions, our potential solutions, are moving away from that solution. So we call that one an unstable equilibrium solution. And one way to think about this is, remember that I said that equilibrium was a kind of balance. If you imagine for the moment that you walk into a room and there's a sword sitting on a huge table, and you walk over to that sword and you look at it, it's at rest. It's just sitting there. It's at equilibrium, right? It's not expending any energy, or you're not expending any energy. to keep it in its current state. Yes, gravity is on and the table is holding it up from the floor and all that kind of stuff. But beyond that, you're not doing anything to it. Nothing is being done to it. If you take the handle of that sword and lift it just a little bit, say an inch off the table, so the tip of the sword is still touching the table, and then you release it, it's just going to fall back to the table. It's going to return to its equilibrium state, right? That's a stable equilibrium. The tendency is for the thing to return to equilibrium. Now imagine that you walk into a room and there's a sword standing on its tip. Somehow, we like to think maybe that it was magic that was doing this, but we know there's no magic. So it must have been somehow the air in the room is just right, and the person who put the sword in that position has been very, very skillful in making it balance right on its tip. All you have to do to knock that sword over is blow on it. Not even that. Wave your hand past it slowly. Any slight disruption in the air around it is going to cause it to fall. It's not going to return to that equilibrium state. It's going to move away from it. That's an unstable equilibrium. Okay, very coarse layperson's description. But when we talk about equilibrium, know that there are these two different kinds of equilibria. There are actually others. There are a couple of cases. I don't know if we're going to see any here, but there are times when you might, for example, see, I'm going to just do a really quick sketch down here. You might have an equilibrium here and slopes above it that are clearly indicating that you would be moving toward that equilibrium. But on the other hand, moving away from it. Okay. And we call that semi-stable. This is a semi-stable or semi-stable equilibrium. Semi means half or part, right? It's partially stable. We're not going to see a lot of that. There are a couple of exercises at the end of the section that deal with semi-stable equilibriums. I'm not sure whether I'm going to ask you to do those as exercises or not. I'll get to that in a few minutes here. But I do want to talk about it because the case, it'll come up, right? The case does exist in which you have not functions moving strictly moving away from or strictly moving towards an equilibrium, but one in which a function might be either moving towards or moving away, and that's called semi-stable. There's one other thing I want to talk about in this video, and that is something called phase lines. I don't actually use these very much. In fact, I think it would be safe to say I really don't use them at all, except as a teaching tool. But it's presented in your textbook. So I want to go ahead and talk a little bit about what they are, and then in a future example, I will use phase lines to sort of help indicate what's going on in that particular situation. But for now, just a quick introduction as to what they are. I'm going to use the same graph, the same function I've got here, the same slope graph and the same slope field to help you see what's going on here. I'm going to put my phase line up here. And I'm going to start by making the observation from the phase graph that y equals 0 and y equals 4 are zeros of the phase graph, which these are also called critical points, by the way. These produce my equilibrium solutions or my equilibrium values. And so I'm going to plot those two values on my phase line. My phase line is really sort of more a reflection or I might call it a preflection, right? This is a precursor to drawing a slope field. So I'm going to mark the equilibrium solutions or the zeros, the critical points on the slope graph on the phase line. I'm going to start with that. And then I'm going to make the observation that all of the slopes between y equals 0 and y equals 4 between y equals 0 and y equals 4, and on my phase line between y equals, down here, y equals 0 and y equals 4, all those slopes are negative. And I'm going to indicate that with a downward arrow. All of the slopes less than y equals 0, less than y equals 0 here, less than y equals 0 here, and so less than y equals 0 here. All of those slopes are positive, and I'll indicate that with a positive arrow, with an upward arrow. And then to the right of, or above y equals 4, above y equals 4, and therefore above y equals 4, again, I have all positive slopes, so I'm going to put an upward arrow there. And from this is our phase line, from this we can tell not only, well, we know what our equilibrium solutions are. We already knew that. They are y equals 4 and y equals 0. But we can see what's happening around each of those equilibrium solutions. We can tell just now at a glance that this is going to be a stable equilibrium, and that because the arrows are both moving towards this 0, and the arrows moving away from this 0, from this critical value, tell us that this is going to be an unstable equilibrium. So the phase line is kind of a precursor, if you will, to making a slope field. I don't see necessarily that you would particularly need to do a phase line if you were going to turn right around and do a slope field. You might find it useful. The textbook uses it as a kind of a precursor to doing this. There are potentially times when you might want to do a phase line and not need a slope field, because you may only want to know whether your equilibrium, which are clear from here, right? You know your two equilibrium values are 0 and 4 from this graph, but you might want to take a quick look at whether your slopes were moving towards or away from an equilibrium, and that might be all you cared about, in which case a phase line might actually be quite useful. I didn't use this space down here after all. This is my phase line here, and that's pretty much all I want to say about it in this video. I just wanted to introduce it. If I bring it up again, it will just be a way of sort of bringing that idea into the conversation that we're having at that time, but I don't know that I'd necessarily ask you for a phase line in an assignment or a quiz per se. But I did want you to see it again. The vocabulary is there. It's used in the discipline of differential equations in mathematics, and you may run into it in the field. And so now I can say that I've introduced that idea to you. All right, well, this video is way longer than I intended for it to be, but that's going to do it for us for now. The next video is going to talk about population dynamics, which is really the other piece and frankly, the main piece of this section.